Okay. Yeah, thank you, Shanwen, for the introduction. I would like to thank the organizers for the opportunity to give a talk at this event. Well, for the last few years, I've been visiting India quite regularly. Yeah, so I'm happy very happy to even remotely to participate in an event organized by the ICTS, which is a wonderful institution. Today I will talk about a joint work. So everything I will say it's a joint work with Adel Bertina and Shengqi Shi. So before I state the main theorem and go into technical details, I would like to motivate a little bit this topic. Because number theorists come from different backgrounds, I would like to somehow illustrate relations between what we are studying and various problems. So the first, okay, so let P be a prime number. It can be 2 for those who like P equals 2, and F. Let's take F be a totally real number field, and let's just for now assume that that P is inert in F. So this will just for the sake of introduction, and actually in the inert case some interesting things happen, so this will come also later, and fix so the first motivation will come from Iwasawa theory. So if you take K over F to be quadratic and quadratic totally imaginary extension, so what's called the CM field. So Katz then constructed a p-adic function which I denote LP. So this is a 1Ks. So this is the Katz p-adic function, the trivial branch. So this is the trivial character. So we are considering the Katz p-adic function at the trivial character. And well, so there is a conjecture which says that the value of this Katz p-adic function at 0 doesn't vanish. So, well, there is some evidence for this conjecture. Maybe put some different color, since that's one of the advantages of giving Zoom talks. So, so one so there is like this is actually a theorem for F equals Q and K imaginary quadratic. So this is if F equals Q, this follows from Katz p-adic analog of the second Kronecker limit formula. So what I have to say is that this value, so this value is related to evaluating the Katz measure. Let's say, okay, well, this is related to evaluating the Katz measure at the trivial character. So this is another trivial. The 0 corresponds to the trivial character. And this character, this is outside the range of interpolation. Because p-adic L functions are defined by interpolation. And so this is why, well, it's not by, we cannot check by definition whether this is 0 or not. But Katz proved the p-adic Kronecker limit formula, and one can see this from this formula. Also, there is another argument which is due to Gross. So there is the so-called Gross factorization. Again, if f equals q. So if f equals q, so Gross's factorization allows us to write this p-adic L function as, okay, maybe let's go to back to black, yeah, f. So this is just for f equals q. To LP, well, the trivial character over q, so this is really the Kubota-Leopold p-adic L function at, so this will be at s equals 1. So at 1 minus s times the Kubota-Leopold p-adic L function of phi omega at s. So what's this is the Teichmüller character, and this is the quadratic character phi of k over q, the quadratic character. So so from here one can see that actually, so this this thing here has a trivial 0 at s equals 0, because since phi of p, oh, I forgot to say the most important, is 1. So I mean, Katz, in order to construct a p-adic L function, he assumes that p splits in k over f. So p, for simplicity, I assumed it inert in f, but then it should split in k. So that's called, the extension is called to have an ordinary CM type in this case. And that's a necessary condition for the existence of Katz p-adic L function. So this thing has a 0, trivial 0, but precisely when this is the trivial character, the Kubota-Leopold p-adic L function has a pole at s equals 0. So at 1, so this is at s equals 0. So a simple pole, a simple 0, they cancel, and that's non-zero. But that's over q. So in general, that's not known. Actually, we will prove this. So that's somehow motivation for people with Iwasawa number theoretic background. So let me now somehow give a different motivation, completely unrelated. I mean, at first glimpse. So we have this character phi. So phi is a finite order Hecke character of our totally real field f, which is assumed to be totally odd. So for example, this can be the above character. Phi can be the quadratic character which cuts this CM extension of F. That's one example, a quadratic character. And moreover, phi is assumed to be what's called irregular at P. So we want phi of P. So P for now, I assume it to be inert. We want phi of P to be 1. So this means that well, P splits in the field cut out by phi. So this is what we call that phi is P irregular. Okay, so in this case, there is okay, so that's second motivation. One can consider a very simple representation. So GF is the Galois group of F. And one can consider a two-dimensional. So all my representations will be in QP bar, just to simplify. Well, there is the two-dimensional representation, which is just given by phi 0, 0, 1. Okay, so this is a reducible representation. This is not P distinguished because phi is trivial. So phi, this condition here, phi restricted to GFP is the trivial character. So this is quite a bad representation from deformation point of view. Okay. It admits, however, universal pseudo character. So let RPS 1 plus phi. So it's the trace of this representation is 1 plus phi, and there is a universal pseudo deformation ring. This is basically just lifts of the trace. So this is just lifts of the function 1 plus phi, which satisfy well the usual properties that one expects the trace of a two-dimensional representation to satisfy. So there is a universal pseudo deformation ring. So this universal pseudo, I should say, like a QP bar algebra, because I'm working in the category of Artinian QP bar algebras. So this is pro-representable by some Noetherian, complete Noetherian local QP bar algebra. Okay, and well, there is a quotient. Okay, not exactly of this. Well, if we pick a root of the so we pick a root. I should maybe put u here because x is used for something else. I pick a root of the Hecke polynomial at p. So I consider u square minus okay. So minus let's call it like tau univ, this universal deformation. So tau univ from p. So I fix a Frobenius, just any choice, just any, plus, well, there is a notion of determinant. That's an exercise that you can always retrieve the determinant from the trace. So there is a quotient of this, which is called R-ord, which classifies pseudo characters which are ordinary at p. So I will, if time remains and if there is interest, I will explain. So this is the Caligari specter. Let's say reduced p ordinary pseudo deformation ring. So just a remark. So this is something. So being ordinary for a pseudo character is a global notion. So it's not just a condition on the restriction of the pseudo character to the decomposition group at P. It's a little bit more subtle, but there is a well-defined quotient like this. And so there is a question. So this is completely representation theoretic question. So there is a question of, well, what is the Krull dimension of this ring? How many reducible components it has? Okay, and so what we can claim is that well, so this ring R ORed 1 plus phi, well, admits, actually it has Krull dimension 1, so the answer is 1, and admits a unique one-dimensional well, component endowed with a well, generically irreducible pseudo character. Okay. Yeah, when you have a pseudo character, actually you can detect from the trace of a representation whether the representation is reducible or not. You cannot distinguish whether it's indecomposable or decomposable, but one can read from the trace whether it's a sum of two characters or not. That's a well-established notion. So that's another point of view. And let me state maybe the third kind of the third possible entry, I mean, motivation for what will follow. So, okay, so assuming this, that there is a unique, okay, so assuming that there is a unique pseudo character, one-dimensional, so actually it will be in values in lambda, so lambda is QP bar. In this talk, it will be QP bar double bracket X. So this is kind of a Iwasawa algebra, but over QP bar. So there is a unique tau like this, a pseudo character, lifting the 1 plus phi, so the pseudo character 1 plus phi, and which is ordinary, which is P ordinary, in the sense of Caligari specter. So it's a quotient of this R ORed 1 plus phi. Okay, so if we denote K to be the fraction field of lambda, each time you have a pseudo character in a field, so we just push forward this to K, this gives, let's call it rho lambda, a two-dimensional representation of GF to GL2 of K, such that, okay, let me write the properties. I mean, so the trace of rho lambda, this is tau. I should maybe call it tau lambda. Then, and the determinant of rho lambda is phi times chi6. So this is the universal cyclotomic character, which takes values in lambda star. And this representation is irreducible. Okay. So note that lambda, so one of the advantages to consider the Iwasawa algebra over QP bar is that lambda is a discrete valuation ring. So when you have an irreducible representation, a two-dimensional representation in a DVR, you can consider the set of stable lambda lattices up to homotopy. And in this case, this is a finite subset of a tree because it's irreducible. The fact that this is irreducible and the fact that rho bar is 1 plus phi, the residual pseudo character is a sum of distinct, so phi is not 1, because phi is totally odd. So this follows that the set of stable lattices is a segment, is a chain like this on the tree. So this is the set of stable lambda lattices is a chain of length r, some integer, in the tree, in the GL2 tree. Okay, I should maybe move in the GL2 tree. Okay, so this here we are imitating Ribet's method for proving the converse to Herbrand, who studied the case instead of lambda, he had ZP and he had some irreducible representation, but which is residually reducible, and he was also considering the set of stable lattices. Okay, so now what's happening is so like in Ribet's method, for each lattice, so these are lattices here, all these points. For each lattice, when you consider the residual, you can reduce. So if you pick like a lattice, one of these points, let's say that's a lattice L, you can consider rho, like, let's say, I don't know how to write it. So for each lattice, Galois of F acts on the lattice modulo a uniformizer times the lattice, which is just isomorphic to QP bar square. And so this gives a two-dimensional representation, right? So for each lattice here. And what's happening is that if a point is an interior point, then, then the residual representation is semi-simple because, okay, that's like in Ribet's method. So all these interior points, it's like this. But the two extreme points, because they have a unique stable sublattice, the residual representation is still reducible but not split. And so this one will be like phi eta 0, 1 for some non-zero eta. So eta is a class, an extension class in HF phi. And the opposite one will be with a lower triangular 0, 1. So where eta prime is an extension in the opposite group. Okay. And here, so from Galois cohomology perspective, one can ask the following questions. So the first question one can ask is what is R? So R is okay. So what's the value of R? I mean, so R actually by it's, for example, very well explained in the book of Belaïch and Chenevier. There is a chapter on pseudo characters. So it's explained that R is it's related to the reducibility, is the valuation of the reducibility LDL. Valuation of reducibility ideal. What this means that R is the biggest integer such that rho lambda modulo x to the R is reducible, is sum of two characters. I should say tau lambda because rho, okay. so tau lambda modulo x to the r is sum of two characters. It's like psi1 plus psi2. So that's an abstract characterization, but the question is, what's the value? And actually, we will prove that it is 2. And a very interesting thing is that the most difficult case to rule out is R being 1, like having only 2 stable lattices. For some reason, the most difficult thing to prove is that R is bigger than 1. Once one can show that R bigger than 1, this kind of implies that R is 2. So that's kind of an interesting phenomenon. Okay, and the second question one can ask is what is eta? Because eta, well, okay, so what is eta? I mean, which is this eta? Because you see, this eta is unique up to scalar, and I want to mention that this extension class, this eta lives in a d-dimensional vector space where d is the degree of f over q. So this unless f is q, this is unless f is q, this is not a line. So it's not clear what's the value of eta. So what is this nice eta that occurs in this deformation problem? Okay, so this was some kind of a motivation in 3 parts, hoping that everybody picked his favorite out of these 3 topics. Are there any questions at this point? Or maybe I don't know whether we are allowed to take questions while being streamed. Anyway, I don't have problems people asking questions during the talk. Okay, so what's the relation between these 3 problems, which are maybe for a novice apparently unrelated? So the relation is the topic of this conference. So the relation is modular forms, and more specifically p-adic modular forms. So these 3 topics touch the theme of p-adic modular forms. And okay, so how we cook up? Okay, maybe I wrote too many notations, but let's go back to the basics. We just had P, which is a prime number, and we had a field F. And let me maybe now allow a little bit. So F is totally real. And let me now really allow phi, which is a little bit more general. So phi is a finite order Hecke character of F, which is it's a rank 1 situation, so such that there exists a unique prime above P, which is irregular, so such that phi restricted to G of V is trivial. Okay, so I mean, phi is unramified at V, and yeah, phi of V it's 1. So this is referred as to the rank 1 case with respect to p-adic functions. This means that the p-adic function of phi will have a simple trivial 0 because just one of the local factors will vanish. Okay. So what can one cook out of a character? Well, if you have a character, then you can write an Eisenstein series. So you can consider a weight 1. So this is weight 1. Eisenstein series, which is attached to 1 and phi. So this is weight 1. So I should say like parallel weight 1, as in Fred Diamond's lectures on Hilbert modular forms. So everything today will be Hilbert. So yeah, the weights are tuples, etc. But this is a parallel weight 1, Hilbert Eisenstein series. So it has some time level, which is related to the, well, of level, actually not time level, of level, which is equal to the conductor of phi. And maybe let's assume that this is co-prime to p. Okay. So once you have such a form, what you can do is you can perform before, we want to p-adically deform, right? There is a p-adic here. So, one has to p-stabilize it, stabilization. Let's call it F. So now, so F is a p-stabilization. So this means that for every W dividing P, the U operator acting on F acts by one of the roots of the Hecke polynomial. So here we choose it to write by F of the phi of W times F. So this is a coherent p-stabilization, because you see, okay, there is the irregular prime where phi of V is 1, but for all other primes, phi of W is not 1. So you can, for each W, you can either stabilize for this eigenvalue or for the other eigenvalue, and you can mismatch. But if you mismatch, then, well, this doesn't deform as an Eisenstein family. So we choose a stabilization which is consistent, so that this F will live in a Hida Eisenstein family. Okay. Okay. So we have this F, and now what can we do? Okay, so we can consider, so F is so what's interesting about F, oops. What's interesting about F is that F is p-adically cuspidal. So what this means, so F, of course, is just a p-stabilization of the Eisenstein series. So it looks pretty much far from a cusp form, like the system of eigenvalues is an Eisenstein system, and etc. But while performing this p-stabilization, actually, we are doing some linear combinations of Eisenstein series. And this killed the values of F at all cusps of the ordinary locus. So this means p-adically cuspidal. So F vanishes at all cusps of the multiplicative ordinary locus of the Hilbert modular variety, if you consider it as a section of a line bundle, like it was explained in previous lectures in this conference. Of the Hilbert modular variety. So one can show that F actually defines a point. This F defines a point. On the Andreatta Juvita Piloni Hilbert eigenvariety. Or in more down-to-earth terms, F belongs to a cuspidal Hida family, if you want. I don't know which language is simpler. So what this means, so we have C. Okay, so E is the D plus one dimensional eigenvariety of Andreatti-Uvita Piloni. So there is a reason why okay, it's cuspidal, I should say. So if you want to deform if you want to put a Hilbert modular eigenform in a maximal dimension family, it has to be a cusp form because Eisenstein series only live in parallel weight classically. So if you want to have a maximal dimensional component, you have to be cuspidal. But and inside this Andreatti-Uvita Piloni, so this lives over a d+1 dimensional weight space. So this weight space is in classifies characters of the torus of F times this. So this is the usual weight space in the Hilbert case, t+1 weights. If you remember from the numerology from Fred Diamond's talk yesterday, so the weight is given by like a K and a W, and K was like a D tuple, and W was some integer such that all the K sigmas were congruent to W modulo 2. I mean, if this is just to, it's not important for today's lecture. It's to just signal the correspondence to what was already said previously. So for us, everything's one. I mean, like for the point we're interested in, and inside there is the parallel weight. So there is a W par, which is just the weights where parallel means K sigma is W for all sigma. So this is one dimensional, and the restriction is just the cuspidal, the ordinary. So this is the nearly ordinary, if you want, Hilbert eigenvariety, and this is the ordinary cuspidal eigenvariety, and this is the full eigenvariety in parallel weight. So the difference between C cusp and C, so these are curves, and the difference is these are curves, eigencurves. But the difference are the Eisenstein components. Okay. Okay, so we're interested in, okay, so maybe I should have written it. So F is a point here. When I say that it's p-adically cuspidal, it's in parallel weight. I mean, it's in weight, the weight says the same under space, so it's in parallel weight, so 1, 1, 1, 1. So F gives a cuspidal point in parallel weight, but then we can deform it in any direction if we want, right? Okay, so we're interested in what happens at F. So somehow all topics I already invoked actually are related to the geometry of the eigenvariety at F. Okay, so so consider completed local rings at F. So I just take this blue diagram and I just localize completed F. Okay, so I have T cusp. So all these are complete local Noetherian QP-bar algebras, which are torsion-free. Yeah, okay, I should maybe first write them. Okay, Okay, so T cusp is the completed local ring of C cusp, and then this is a quotient of T nearly ored, and there is T here, which also suggests like this. And this is a lambda algebra. Okay, so lambda is really the lambda that we already saw. So lambda is isomorphic to QP double bracket X. And I choose an uniformizer so that X equals 0 corresponds to, so this weight map, let's call it kappa. I mean, this is the weight map, to kappa of F. So this is the weight. This is 1 if you want. Okay. And here we have, oops. I don't know, sometimes they're it's slow. Okay, so there is lambda nearly ored. Okay, so these maps here, the vertical arrows are finite flat. Okay. Okay. Right. So I think we are ready now to state the main result. Well, so the main result, as advertised, is about the structure of the eigenvariety at Hilbert Eisenstein point. So it's about these rings, because these are the complete local rings of the eigenvariety at F. I mean, there are 3 eigenvarieties. There is the full dimensional cuspidal, the one-dimensional cuspidal, and the one-dimensional, like the parallel weight total eigenvariety. I mean, yeah, that includes Eisenstein components. Okay, so let me say the main theorem. So there are 2 assumptions. So first, assume that the Leopold conjecture let's say the Leopold defect at, the Leopold defect at P of F vanishes. Okay, so another way to state this is that the continuous QP bar homomorph the continuous homomorphisms from GF to QP bar is just a line, which is actually, we will use the generator, is generated by eta 1. So it's generated by the log of the cyclotomic character. So that's the equivalent, that's what this means. And recall that we are in a rank 1 situation, that there exists a unique V dividing P such that phi of V is 1. So this was already stated above. Okay, so those are the assumptions. Then the geometry of this eigenvariety, of those eigenvarieties, is dramatically different depending on the degree of the local degree of FV of F at V. So if V is the unique prime above P, or almost the unique prime, so if the local degree is at least D minus 1, so there is a unique prime above P, or maybe there are 2 primes, but the other prime really it just gives QP. Then then T cusp, then T nearly ored, let's say, is étal over lambda nearly ored. I mean, hence this is equivalent. Hence, T T cusp is etal over lambda. And in terms of Hida families, this means that there exists a unique irreducible component. There is a unique cuspidal Hida family. Hida cuspidal family passing through F. Okay, and there are one or two Eisenstein families passing through F, depending whether degree is F over Q or F over Q minus 1. So this is kind of the nicest case. I mean, in this case, if I draw a picture, so there is like F, and this is a picture which is in C. So there is a unique cuspidal family, which I call F, and there is always this Eisenstein family E1 phi, and there is another Eisenstein family if the local degree is maximal. So this other family only exists if there is no regular prime. So if V is the unique prime above P. So this one only exists, it always exists, but it passes through F if F V over QP is F over Q. Okay, maybe I can, okay. Could have written this, okay. Okay, so that's somehow the nicest case. Then there is a second case, like kind of the opposite case. If the local degree is just QP, then T-Yord is smooth. Hence, T cusp is complete intersection, right? So this is like a regular ring. I mean, smooth means regular ring. And if it's a regular ring, the recipe from quotienting here is going modulo the kernel of lambda near Yord to lambda. And this is quotienting by a regular sequence. So if you take a d plus 1 dimensional regular ring, and if you quotient by a regular sequence, you find a complete intersection. Okay, so and the remaining case, so in the remaining case is when FV over QP, the degree is at least 2, and at most F over D minus at least 2, and at most this. So the local, I mean, this happens if the degree should be at least 4. I mean, otherwise this case doesn't happen. Well, then actually T-Yord, we were quite surprised to find this, but actually T-Yord is never smooth. And T is not smooth either. So yeah, this is in striking difference with the case, let's say over Q, where well, things sometimes are not at all, but they're always smooth. But yeah, so T cusp is not smooth either. Okay, so and actually, just to make a remark, so in this last case, the way we show that this is not smooth is that it doesn't exist. Okay, let me write. Actually, this is interesting. Let me put it as part of the theorem. In this last case, so in the third case, more precisely, for every minimal prime P in T-Yord, minimal prime. So the minimal primes in this local algebra corresponds to its irreducible components and corresponds to the Hida family's modulo Galois conjugacy. So the statement is for every minimal prime, there doesn't exist a Galois representation in GL2 of T nearly ordered modulo P. I mean the ordinary Galois representation, nearly ordinary. Which realizes the universal pseudo character, realizing the universal pseudo character. So the universal pseudo character is T nearly ordered, goes to T nearly ordered modulo P. And why this proves the claim? Because well, if a ring is regular, then it's factorial, and once you have a factorial ring, you can always you can always conjugate a representation which has values in the fraction field and which has trace in the ring. You can conjugate it if you're in a factorial ring. You can always conjugate it to be in the algebra. So there is really I mean, so it's a Galois theoretic kind of abstraction for T nearly ordered to be smooth. Okay, so in the remaining 7 or 8 minutes that I have, I would like to maybe okay. So first, okay, let me first say that so analog of this main theorem was proved when F equals Q by Adel Bertina, myself, and Alice Pozzi a few years ago. But the techniques we use here are quite different because okay. Well, one of the ways to study for let's say for F equals Q, we approached T cusp by a Galois deformation problem. By a Galois deformation by phi eta 0, 1, actually comma phi eta prime 0, 1, which was possible because in this case the dimension of the Galois cohomology was 1. So there was a canonical eta and eta prime were canonical. And because they were canonical, we could define deformation, ordinary deformation problem of these things and prove R equal T theorem. The approach is completely different here. Actually, we tried studying different deformation problems and most of them failed. And then we decided to focus on Hida's nearly ordinary Hecke algebra and the universal pseudo character that it carries. So the approach here, okay, so let me sketch. Oh, I really have 5 minutes, so it will be a brief sketch. Let me sketch a proof of 1. So proof, let me sketch a proof when P is inert. And actually, this is the case which has application to the first application I gave about the non-vanishing of the Katz p-adic L function at the trivial character. Let me make a sketch when P is inert, so when Fv is Qp. So this is like P, let's say P inert in F. Okay, so in this case, we want to show that T cusp is et al, and it's equivalent to T nearly odd being et al over lambda nearly odd. So what we do, we start by the pseudo character, which is given by the theory of Hida, worked out by Wiles. So we have a pseudo character in T nearly odd. So this is a two-dimensional pseudo character, and so this gives rise to a GMA. Well, what this means? So if you denote K, the total fraction field of T nearly odd. So they may be many components. It's a total fraction field. I mean total. So Hida and Wiles give a representation rho K. Let's call it ABCD from GF to GL2 of K, which lifts tau. So this means that the trace of rho K is tau. Also rho K of the complex conjugation. Oops. The complex conjugation is like -1,1. And okay, and we fix the determinant as usual. So the determinant is phi times the universal cyclotomic. Okay. And now there is information here, which is that we know, I mean, by the theory of Hida and Wiles, because F was an ordinary point. So this is nearly ordinary. So what nearly ordinary means? This means that there exists a matrix AV, BV, CV, DV. Okay, so okay, I should have put AP. Okay, let's simplify. AP, I mean V is P, right? Such that when you conjugate rho K by this matrix, you find upper triangular matrix. This is on the decomposition group at P. Okay, this is P. Okay. Right, and so then there is a technical lemma, which was, well, first in this case proven by Darmon, Dasgupta, and Pollack, which is actually that AP and CP are non-zero divisors, so they're in K star. This is a total fraction field. This is a product of fields. This is a product of KIs, if you want. And moreover, CP over AP times B of G is in the maximal ideal of T nearly odd, and AP over CP of C of G is also in the maximal ideal. Okay, so what this means? This means that you can conjugate rho, right? You can consider A prime, B prime, C prime D. You can conjugate rho by CP over AP, because this is a non-zero divisor, so you can conjugate rho K by this matrix. And now it will go in GL2 of T nearly odd, And moreover, if you go modulo the maximal ideal, well, it will reduce to phi 001 because both the, so this is B prime if you want, this is C prime if you want, C prime. Both are in the maximal ideal. So this shows actually that the, in particular, the reducibility ideal is at least 2 because both are 0. Okay, so let me then conclude. So how the proof of this? Maybe I just take 2 minutes, not more. So how do we conclude? So you take this new representation, and you push it forward by a home from the tangent space. So we want to show that it's étal. So we want to show that that any homomorphism from the relative tangent space to this is constant. We want to show that this is QP bar, right? So we want to show that if we push this forward by a homomorphism like this, it's a trivial deformation. So we show, if you push forward this representation by a homomorphism, you find the infinitesimal deformation, which is 1 plus epsilon A epsilon B epsilon C epsilon D epsilon, like phi 001. Well, and here actually what you show is that you show that you show that A epsilon is minus D epsilon is eta 1, and you compute actually B epsilon restricted to the inertia is minus A epsilon restricted to inertia equal to C epsilon restricted to the inertia. So this determines uniquely B and C, and a third and final relation. So this determines B epsilon and C epsilon uniquely. And a third relation actually shows that, okay, here I'm going a little bit fast, that the L invariance, that there is a condition on the Frobenius, so evaluating at Frob V, at Frob P, we found this relation for the algebraic L invariance. So these are kind of log of some algebraic numbers, and this contradicts Baker-Brummer. Okay, it's a proof of a contradiction because I should have said, I mean, you can write this if A is if this is non-zero, and if this matrix is 0, then you're done. Okay, so this implies that rho epsilon is rho, and this implies that T nearly ORD is lambda nearly ORD, and okay, that's okay. I'll stop here, and we'll take questions, if any.
If there are no questions or remarks, let's send Professor Dimitrov again. Thank you for your wonderful talk.